Okay, this video is going to look at the integrated math day 16, number 4. It's the problem about a geologist driving through the desert and trying to get to a gas station. So I've drawn the diagram here, and we're starting at point A, the gas station is point P, and the problem is walking us through a couple different scenarios. The first one, so part A, asks how long it would take to go from A directly through P. So I'll draw that as a red path, and we'll make it dotted. So if we were just to go from A directly to P, how long would that take? And there's some information that I haven't written down here, such as how fast the geologist can drive through the desert and how fast the geologist can drive on the road. This blue line down at the bottom is representing our road. So this red dotted line is desert all the way, and we know we can drive 30 kilometers an hour in the desert. So to solve this, what we're going to need to do is look at this equation that I'm sure you have seen before. Rate times time equals distance. And we're not solving for distance here. Instead, what we need to do is find out how long it'll take. So we're solving for time. So what I'm going to do is divide both sides by r so I can get time is distance over rate. So if we find the distance that we're traveling and the rate that we're traveling at, we should be able to find how long it takes. Well, it looks like the rate we've already got. So we don't know what the distance is yet, but we're going to find it in a second. I know that that rate is going to be 30 kilometers an hour. And for a distance, what I'm going to do is, well, I think I see a right triangle here. Let me draw that in. There's a right triangle, and I know the sides of the legs, and I'm looking for the hypotenuse, so that looks like Pythagorean Theorem to me. So I know that 10 squared plus 20 squared is going to be, let's call it c squared. So if I square root both sides, 100 plus 400 is going to be c. So I could write up here, let's call it root 500. That can be simplified, but I don't think we really need to. So let's see. I guess we can put that into our calculator. Root 500 divided by 30 is going to be 0.7454. We can just get a decimal approximation here. It's asking for us to solve it to the nearest tenth, so it's okay to do a decimal. Oh, 7. Let me erase that. 7.454, let's say. And that represents hours, right? So because I've got hours in my units here, so I'm going to need to multiply that by 60. So this is hours, and to get minutes, I'll multiply by 60, and I'm going to get 44.7 minutes. So that's how long it's going to take me to go from A directly to P through the desert. The next part, and I'll just put it up here, so let's put part B, asks how long it would take to go from A to N and then from N to P. So this is going to use the same thing. We're going to use time as distance over rate, but we have two different distances and two different rates that we're going to add up. So first, let's go from A to N. So A to N. And this let's call it T1. And that's going to be the distance from A to N. So I think we can call that 10 kilometers. And the rate. So we're still traveling through the desert here. So my rate is going to be 30 kilometers an hour. And so that's going to be a third of an hour, or let's turn it into minutes, 20 minutes. Okay, and T2 is from N to P, so we're along the road. We know it's 20 kilometers, and our rate here is 50 kilometers an hour. So we can turn that into 2/5 of an hour, and in minutes that becomes 24 minutes. Okay, so now let's look at part C of this problem, where we're asked to find an even faster route for Alex to follow. So how are we going to do this? Well, we have to think about what a faster route might look like first, I suppose. So if we know that we're going 50 kilometers an hour, that looks messy, but you get the idea. And if this is 30 kilometers an hour, I think it makes sense that we want to get as much 50 kilometer an hour time in as we can. So in other words, I think we want to get to the road really fast. So I would propose that a route that went somewhere like that probably wouldn't be the best. You know, it's not very direct. We looked at this route, right, which was a direct route, but it was all desert driving, and we saw that that took longer than going from A directly to N directly to P. So the A to N to P was faster, but let's see if we can get even faster than that. And what I propose is, I'll do it in red, what I propose is we find some route here. Now, what does that do? Well, that gets us to the road pretty quickly. Not as quickly as going directly to N, I agree, but it gets us closer to our destination. So we're getting to the road quickly, and we're kind of going along our way as we get to the road. So I think there's going to be some happy balance where we don't go directly straight down to N, we go a little bit towards P, but we still don't want to go all the way to P. So this angle is going to be a lot sharper. So we're going to try and cut towards the road faster. So that's my guess. Now, how the heck do we know if we're right? Well, we've got to try and find some relationship here that we can use. And what I'm going to do is try solving the equation almost the same we did before by adding up the time through the desert and time through the on the road. But we need to define some things first. So first of all, let's say, okay, there's a distance here between where I hit the road and N, and I'm going to call that X. And the reason I'm calling that X is because I don't know how far along the road I'm going to hit. I just am guessing that, you know, there's somewhere over there that is going to be the fastest way. So if I call that X, then I need to find out how long I'm on the road. And since from N to P is 20, I think I can call this 20 minus X. And that'll be how long I'm traveling on the road with my new route. This distance is still going to be 10 from A to N. So I need to find an expression for my red segment there, the segment along the desert. And I think I see Pythagorean Theorem again. It's a smaller triangle than I did before, but I think I can still do it. So let's say 10 squared plus x squared is, I'll call that distance c squared, my hypotenuse. So 100 plus x squared is going to be that distance. So I'll try and write that in there. Oh, square root, of course. So square root 100 plus x squared. All right, so I think I can find, using my, again, I'm going to keep bringing this up, rate times time is distance, so time must be distance over rate. So my time total is going to be the sum of two different distances, like in the previous part where we were going straight from A to N, and that was a certain time, and then straight from N to P, and that was another time. So let's find that red time first. Let's call that T1. Actually, I'm going to move further. Let's call this, there we go, T1. And that's going to be my distance over my rate. And the distance we said was the square root of 100 plus x squared. And my rate, we're going through the desert, so I'm going to call that 30. All right, doesn't look pretty. I can't really simplify it, so we'll just leave it like that. T2 is going to be what? Well, I'm going how far on the road? I think 20 minus x works, and that speed is going to be 50. So if I want to find my total time here, I'll say, let's just call it T tot. And that's going to be the sum of those two times, right? Because I'm going to go through the desert and then on the road, and my total time is going to be the sum of those. So square root 100 plus x squared over 30 plus 20 minus x over 50. And I'm saying that this is going to model my total time for this path. Now, what's interesting to check here, we've got a function of time with respect to x, okay? And x is the thing I can change. It's my independent variable. So let's see what happens if I let x be, let's let x be 20, all right? So that would model what? If I let x go all the way to 20, that's the same as going from A to P, right? Because that red line is going to start shifting this way until it matches that dotted line there. So let's see, if I let that be 20, what happens to, let me go to red again. What happens to this term if x is 20? That becomes 0, right? That goes to 0. So we're just left with this square root of 100 plus 20 squared, which is 400 over 30. That becomes our root 500 over 30, which we saw in the previous part of the problem, ended up being our answer for that. So that's nice. What happens if, let's get rid of this real quick. What happens if we let x be 0? So when x is 0, that means that's modeling, right? So this time we're going to shift, let me get my white. Okay, this time we're going to shift this way, and we're just going to go from a right down to n because our x is 0. Now what happens here is we get a mix, right? We get the root 100 over 30, right? And we get 20 over 50. And from the previous problem, that's going to give us our 10 over 30 and our 20 over 50, which is how we added up that total time. So this actually models the two situations that we've seen before. And so that's pretty interesting. And so now what we need to do is we need to find how we can make this the fastest possible. So right now, we don't have the tools to do this without graphing. Eventually, you'll get into some calculus where you can take a derivative, don't worry about that right now, where you could find it without having to graph it. But we need to graph it now. So I went ahead and graphed this, and I'll just do a little sketch here. So it looks kind of scary, but if we graph it, there's something that looks like that. So what have we graphed? Well, this is t as a function of x, okay? So x is going to be along this axis. These are our x values. And what is on our y-axis here? Well, that's going to be t values. So those are certain times that we get whenever we put in an x. So somewhere on here, if we put in x is 0, we get that time from part A, and then, B, excuse me. And if we put time is 20, we get the answer from part A, where we just went right from A to P. And then somewhere, the fastest time lives, I'd say it's right about there. And your calculator can find this exactly, and it does. And there's a point there, and I'm running out of room, so I'll just draw an arrow. That point is the minimum time. Does everyone see that? So it's the lowest that the function gets. And it turns out the coordinates of that are 7.5 2/3. Okay, what does that mean? Well, the x value is 7.5, which means that we're coming from A down to the road 7.5 kilometers away from N. So that x value there that we had in our diagram is 7.5 kilometers. So that's interesting, all right? That's in the ballpark, right? It should be between 0 and 20, and it is. And if you look, 7.5 is going to be closer to N than P. So our kind of guess works. Now, what's that 2/3 there? Well, since y is the t values, that's the time that it takes when we go from A to a point on the road that's 7.5 kilometers from N, and then go right to P from there on along the road. So that's how long it takes. And remember, it looks a little weird, I guess, 2/3, but our units here are in hours, right? Because our rate was kilometers an hour. We didn't convert it to minutes. So this is 2/3 of an hour. Let's say 2/3. Oops, that wasn't the eraser. 2/3 of an hour. So we can call that, what, 40 minutes? And is this, in fact, faster than our other two routes? Well, I think so, because the first one took 44.7 minutes. The next one was a little faster at 44 minutes. And we got down to 40 minutes. And I don't think we're going to be able to do any faster than that. So this was an interesting problem. There was a couple easy parts to it, and then we really had to start thinking. And we got a lot of practice with our functions and how to find the minimum value of a function using our calculator.